So the next topic is automorphism groups and fixed fields. So first of all, let me check what is the definition of automorphism group. So for automorphism group, we have this definition that suppose F is the given field, F is given to be the field and E is the extension field of F. Then the group of automorphisms of E leaving each element of F as fixed is called the group of F automorphisms of E, and it is denoted by G of E by F. We'll understand this in a moment, that what exactly is this automorphism group. So you can understand it in this way, that you have some field, then you have the extension field for that E. Then we are defining some mapping from E to E. Suppose sigma is the mapping from E to E. Now they are saying this mapping is an automorphism. That means the mapping is defined from same field to same field. It is 1, 1, it is onto, and it is homomorphism. If all these conditions are satisfied, your mapping would become isomorphism, and because it is defined from the same field to the same field, it is finally called automorphism. Okay, so we have this extension field, so we are defining some mapping from this extension field to another extension, to the same extension field. So there would be many such mappings. So when you collect all these mappings into a set, this is the set of all automorphisms. So this set is called as the F automorphisms of E, the group of F automorphisms of E, and we denote this by G of E by F. E by F means E is the extension field of the field F, and G means this is the group of automorphisms of all the consisting of all the automorphisms, that is, it is consisting of all the mappings which take E to E, and it is a isomorphism. And next let us define fixed field. What is a fixed field? Suppose E is any field and H be the subgroup of the group of automorphisms of E. Then corresponding to this subgroup, we define a field EF, E of H, right? Where H, as soon as this H changes, your field changes. So this is depending upon H. So what does this say? It says that if you take some member from H and then you apply that member to some element of E, that means this sigma of X, so you will get that element back. So that means the mapping sigma is not changing this particular element X. It is keeping this element fixed, where what is this element? X element is coming from the field E, the extension field, and the sigma mapping is coming from the group which we have created for automorphisms, and this is the subgroup of that group of automorphisms. So when this happens, the collection of all the elements which are kept fixed under such mapping, that is known as fixed field of group automorphisms of E. So the name itself suggests that this mapping, all the mappings which are present in this set H, in this group H, they those mapping are keeping all the elements of E, as fixed. So this is the definition for fixed field. So let us now understand the meaning exactly, what is happening, what all things are with us, and how we are linking up the things. So I am saying I have this mapping as F, I have this field as F. Now we are constructing an extension field E of F. Now what we are doing, we are creating, or we are defining the automorphisms by the mapping sigma from E to E. This is one mapping, say sigma 1. Then we have another mapping sigma 2 from E to E. Then we have another mapping sigma 3 from E to E. And we have so many mappings sigma n from E to E. All these mappings, they are defined from the set E to the field E, from the field E to another field E. Now what you do, you collect all these mappings into one particular set. So this is our set. Now this set together with the operation of composition forms a group. That means it will satisfy the closure property, it will satisfy the associative property, then it will satisfy the identity property and inverse, existence of inverse for every element, for every mapping. Here the elements of this set, elements are mappings or functions, and the operation that is defined here is that of composition. That means you are doing composition of one mapping of another. That is the operation that is being performed. So identity would be the identity for this group would be the identity function, which does not change anything, right? And the inverse would be the inverse of that particular function. So this forms a automorphism group, and what we are doing, we are saying, now what we do, we take some very small portion of this particular big group. So that is, I am calling that as H. Now this also contain automorphisms, because this is nothing but a subset of the given set of automorphism. This is automorphism group. So we are taking a subset for this one, and we are calling this to be the subgroup of the group G E by F, the group of automorphisms of E. Okay, so this is one thing. Another thing is that this is about the subgroups and groups. And what about fixed fields, and how are we defining it? Now you had this F here, this was some field that was given to you, this was the given field, and then we had an extension field over here as E, this was the extension field. So what we are doing, we are taking this element H, we are taking this subgroup as H, it consists of the automorphisms. That means it consists of all the mappings. So corresponding to this H, we are constructing one subfield over here, or one field over here, or one set over here, calling that by EH, so that whenever you take some element E, X from E, some element from here, the mapping taken from here would leave the element as such. So this forms an intermediate field. This EH, this forms an intermediate field between this field E and the field F. So this is the relationship that joins the groups, the subgroups as in the automorphism groups and the corresponding subfields. So this is the subfield of the given field E. So we say that finally every subgroup H of this Galois group of automorphism E over F creates a subfield EH of E such that every element of F is kept fixed under the automorphism mapping. So in short, what we are doing, this was our field F, this was our field E. Okay, so what we are doing, we are constructing some set over here, collecting all the mappings. This is the set of mappings, and this is nothing but this is the group of automorphisms. This group keep elements of F as fixed. That means the mappings which are present in this particular set or group, they are not changing any element of F. That means they act as identity over F. So and by in notation this is defined like this. Now what we are doing, we are taking some subset of this one, we are calling this to be H. So it will by default contain all the mappings which are isomorphisms from E to E, and corresponding to this H we are constructing some field over here EH. This is the fixed field, and this lie between E and H such that whenever you take some element E of X of E, then the mapping taken from here, you call this by sigma or by phi, whichever name you would like. So sigma of X would be kept as X only for sigma belonging to H. So that is what it means to be an element of this. So the collection of all such elements is known as the fixed field. So here you saw that there is a beautiful relationship. So this is about fields and subfields, and this is about groups and subgroups. So there is a beautiful relationship between these two, and this relation is defined very well by the fundamental theorem of Galois theory. That we shall study later on. Before that, we shall first see this terminology and see various examples and the properties of the corresponding fixed fields, and we'll see several examples for the same.